Welcome to This Explainer. Today, we're tackling one of the absolute most fascinating challenges in all of mathematics. Seriously, we're talking about translating messy, real-world unpredictability into structured, understandable data. We are basically going to decode the underlying rules of chance. Okay, let's dive into this. How do we actually mathematically measure the unpredictable? I mean, whether it's the chaotic outcome of a gamble, a sudden shift in the weather, or trying to predict complex logistics for a massive supply chain, dealing with uncertain outcomes is just a fundamental problem we all face. We really need a way to quantify what we don't know. So here is our roadmap for getting there. First, we'll meet the random variable. Second, we'll look at discrete probability. Those are the countable outcomes. Third, continuous probability, or the infinite possibilities. And finally, we'll bring it all together with expectation and variance.
All right, part 1. Meet the random variable.
At its core, a random variable is just a variable that can take any value determined by the outcome of a random event. In plain, everyday language, it's basically our mathematical placeholder for chaos. Instead of just throwing our hands up in the air and saying, well, we don't know what's going to happen, we assign a variable, usually we just call it x, to represent all the potential outcomes of that completely uncertain event.
Let's anchor this math to a concrete everyday example. Think about tossing a coin. The outcome isn't fixed, right? We have no clue if it'll land on heads or tails. But we can map those outcomes mathematically. If we declare our random variable, x, equals 1 for heads and 0 for tails, we have literally just turned a physical, totally uncertain flip into a clean, trackable number.
Now, when you're getting into probability, you might hear the term frequentist thrown around. Honestly, don't let the jargon intimidate you. The frequentist view simply asks, how frequently do we expect different outcomes to occur if we just repeat the experiment over and over again? It's really just looking at the long-run average. If you flip that same coin a million times, that long-run repeating behavior is exactly what we're trying to map out.
So, the crucial point is understanding the big split in probability, discrete versus continuous variables. This distinction dictates exactly how we measure our random outcomes. Discrete variables are things that take on countable, very distinct values, kind of like the distinct sides of a coin. Continuous variables, on the flip side, take on an infinite number of possible values, meaning they are things we physically have to measure rather than just count.
Which brings us to part 2, discrete, the countable outcomes.
Just think about people waiting in a line. You can physically point and count them. 1, 2, 3 people. You absolutely cannot have 2.5 people. That is discrete. It's the same for the number of sales made in a day or mistakes on a page. Now contrast that with time on a clock. Time, weight, volume. These don't just hop from one whole number to the next. They flow smoothly, passing through infinite continuous fractions.
Focusing strictly on those countable discrete variables for a second, let's look at rolling a standard 6-sided die. Because rolling a 1 through 6 are all equally likely outcomes, a probability mass function maps this out as a perfectly flat line. Every single outcome has exactly a 1 in 6 chance. And crucially, if you sum all those individual probabilities together, they have to equal exactly 1, no exceptions. Let's move to and see how this builds with a cumulative distribution function, or CDF. Instead of looking at individual outcomes in isolation, a CDF adds them up as we climb the numbers. So the probability of rolling a 1 or 2 is 2/6. Rolling a 1, 2, or 3 is 3/6. It transforms our flat data into this rising staircase that ultimately tops out at exactly 1.0 once every single possible roll is accounted for.
Let's actually apply this to a real-world dynamic logistics problem, predicting the arrival of ships at a busy harbor. The number of ships is a countable, whole number. I mean, a half-ship arrival isn't a delivery, it's a shipwreck, right? So this scenario is perfectly modeled by a discrete random variable.
Here is the probability distribution for our harbor, mapping the number of ships, which is our x, against the probability of that exact number arriving, our p of x. Let's solve a quick one together. What's the probability that exactly 14 ships arrive? Just check the data. For 14, the probability is 0.1 or 10%. What about at least 12 ships? Well, we simply add the probabilities for 12, 13, and 14 together. 0.2 plus 0.1 plus 0.1 equals 0.4. Just by reading the data, we can start to manage the absolute chaos of our supply chain.
Moving right along to part 3, continuous, the infinite possibilities.
When we shift gears to continuous probability, we're suddenly dealing with infinite possible measurements. Because of this, we just have to stop counting individual data points altogether. Instead, continuous probability is mapped by a continuous mathematical function, sweeping across a graph, where the total area under that entire curve is always, by definition, exactly 1. And this brilliantly illustrates the concept. Consider this overarching negative exponential curve. It's a super common function for continuous distributions. Now, because a variable could land on literally any infinite microfraction along that line, the probability of hitting one exact specific point is mathematically 0. Instead, calculating a continuous probability simply means finding the area of a shaded region between two specific points under that curve.
To find the exact area of that shaded slice from point 1 to point 2, we use calculus, specifically integration. Now, for anyone who might be new to this level of math, please don't worry. The integration formula here might look a little intense, but it's really just the mathematical engine we use to calculate that shaded slice. By integrating the exponential function from 1 to 2, the math churns out a result of roughly 0.23, or a 23% probability.
And finally, part 4, expectation and variance.
Every single probability distribution we've talked about today is characterized by its expected value and its variance. Expected value is exactly what it sounds like. It's the average or mean behavior of our random variable x over the long run. You can think of it as our ultimate mathematical anchor. It tells us exactly what to expect if we just let the chaos play out indefinitely. Notice how perfectly the formulas for these two variables mirror each other. For a discrete variable, the expected value formula uses a summation symbol because we are literally adding up distinct countable outcomes. But for a continuous variable, the formula swaps in an integral symbol because we're calculating an infinite continuous area. The underlying logic is completely identical. We're just picking up a different mathematical tool. To really grasp expectation and variance, let's look at the ultimate real-world test of these mathematical laws, the casino roulette wheel. A standard American roulette wheel features the discrete numbers 1 through 36, plus the specific house pockets of 0 and 00. Guys, this isn't just a glamorous game of chance. It is a meticulously constructed probability distribution designed to behave a very specific way.
Now, what's really interesting about this slide is how we can actually manipulate these variables using the mathematical properties of expected values and variance. If you change a system, say a casino modifies its payouts by multiplying them by a constant, or maybe subtracting a fee, these formulas tell you exactly how the mean, expectation, and the spread of the risk will instantly shift. It's a completely actionable mathematical toolkit for adjusting systems of chance.
Which brings us to a final, provocative thought to leave you with today. If a casino understands these exact expectation and variance formulas perfectly, mapping out the precise long-run average of every single spin of that wheel, how do they design the payouts to ensure the house always wins in the long run? Think about it. The chaos of the spinning wheel is just an illusion. Underneath it all, the random variable is doing exactly what the math predicts. Thank you so much for joining me on this explainer, and I really encourage you to keep looking for the hidden math in the unpredictable world all around you.